All right, welcome back to our quantum series. Today, we are diving headfirst into one of the absolute weirdest, most mind-bending experiments in all of physics, the delayed choice quantum eraser. Seriously, this is an experiment that seems to grab our understanding of time and causality and just tie it into a knot.
I mean, it all comes down to this one question, right? It sounds like something straight out of a movie. Can an action you take right now somehow reach back and change something that's already happened? It feels impossible. But this is exactly the kind of puzzle that quantum mechanics makes us look at straight in the eye. So to get to our heads around this, we have to start with the classic, the double-slit experiment. You've probably heard of it. As you can see here, if you shoot little things like photons at two slits and you don't look, they act like waves. They go through both slits at once and create this beautiful interference pattern on the other side. But, and this is the crazy part, the second you put a detector there to see which slit it went through, bam, the wave behavior vanishes. They act like little bullets, and you just get two clumps. The very act of looking changes reality. And that, of course, leads to the big question, the one that physicist John Wheeler couldn't stop thinking about. What if we cheat? What if we wait? We let the photon pass through the slits, presumably as a wave, doing its wave thing, and only after it's already through, we decide to check which path it took. Does it somehow change its own past to say, oh wait, I was a particle all along?
So how do we even start to unravel this mess? Well, we need a new way of thinking about it. It turns out this isn't really about the physical act of observing. It's about something much more subtle. It's about information.
Yeah, this is a really key shift in understanding. The old way of thinking, from Heisenberg, was that measuring something always meant you had to poke it, right? You'd physically disturb the particle, and that's what messed up the wave pattern. But the new idea is way spookier. It says you don't have to disturb it at all. The mere existence of information about which path the particle took, even if nobody ever looks at that information, is enough to kill the wave behavior. Just knowing the information could be known is what does it.
And this gets us to a core quantum idea called complementarity. In plain English, this quote just means that knowing the particle's path and seeing the wave's interference pattern are locked in a trade-off. It's one or the other. You can know where it went, or you can see the wavy pattern it made, but you can't have both at the same time, period.
And of course, physicists have turned this beautiful idea into a tidy little bit of math. It's called the Engler-Greenberger duality relation. Now, don't worry about the squares and stuff. The concept behind it is actually super simple. It perfectly describes this balance between being a wave and being a particle.
So let's just break it down. D is for distinguishability. That's just a fancy word for how much path information we have, how well we can distinguish which path it took. V is for visibility, which is how clear our wavy interference pattern is. The formula basically says they're on a quantum seesaw. If D goes all the way up to 1, meaning we know the path for sure, then V has to be 0, no pattern. If V is 1, a perfect wave pattern, then D must be 0. We have no clue which path it took. Okay, so you got it? It's all about information. With that in our back pocket, let's look at the experiments that seem to use this idea to actually reach back and change the past.
This is the basic layout for Wheeler's experiment. A single photon comes in and hits that first beam splitter, BS1. That puts it into a superposition. It's now traveling along path X and path Y at the same time. The delayed choice happens way over on the right. We can either put that second beam splitter, BS2, in its way or pull it out. And the key is we make that choice while the photon is still in the middle of its journey, when it's in flight. And check out the two results. If we take that second beam splitter out, the detectors just tell us which path the photon came from. It behaves like a good old particle. We know its path. But if we slide that beam splitter in at the last second, it forces the two paths to cross and interfere with each other. And when that happens, something amazing occurs. Only one detector, detector Y, ever clicks. The photon acts like a wave that went both ways at once. It's like our choice now determined whether it was a particle or a wave back then. But the quantum eraser experiment, oh boy, this takes things to a whole new level of strange. It's designed to let us erase the which path information, not just after the particle chose its path, but after it has already hit the detector, after its journey is completely over.
So here's how it works step by step. First, we create what are called entangled photons. Think of them as quantum twins. What happens to one instantly affects the other. We call them the signal and the idler.
The signal photon is our main character. It goes through the double slits and hits our main screen. Its twin, the idler, is our little spy. It carries the witch path information. We send the idler on a much, much longer path to a whole different set of detectors. And here's the kicker. We make our choice to either keep or erase the idler's path info long after the signal photon has already hit the screen and become a permanent part of the data.
So is this it? Is this finally proof of retrocausality? Did we just find a way to edit the past? Well, here comes the big reveal. And the answer is weirder and cooler than simple time travel.
Because here's the first thing you notice. If you just look at the raw data from the main screen, all the little dots where the signal photons landed, you see absolutely nothing. It's a meaningless random splotch. There's no interference pattern. There's no two-clump particle pattern. There's just a mess.
The secret isn't in changing the data, it's in how you look at the data. And this quote from Physics World has the perfect analogy. It's like you're watching a 3D movie without the glasses. All you see is a blurry, jumbled mess. On the screen, the measurements we make on that other photon, the Euler twin, are the 3D glasses. The glasses don't change the movie that's being played. They just let you filter the light so your brain can see the two separate images that were there all along.
So this quantum eraser isn't some magical time machine. The measurement we make on the idler photon just gives us a tag, a piece of information. We then use that tag to go back to our big, messy pile of data from the main screen and sort it into different buckets. It's a sorting process, what physicists call post-selection. And when we do that sorting, wow, we say, okay, computer, only show us the dots from signal photons whose idler twins landed in, say, detector A. And boom, out of that random noise, a perfect interference pattern just emerges. It was hiding in there the whole time. But here's the other half of the magic. We then say, okay, now show us the other dots, the ones whose idler twins hit detector B. And what do you know? Another perfect interference pattern appears, but this one is the exact opposite of the first one. The peaks of this pattern line up perfectly with the valleys of the other one, and suddenly it all makes sense. The reason the total data looked like a random blob was because these two perfect opposite patterns were layered on top of each other, completely canceling each other out. So the big takeaway is this: the past isn't being rewritten. Not at all. The signal photon hit the screen where it hit. That event is frozen in time. What our delayed choice does is it gives us new knowledge about that past event. We gain the key, the 3D glasses, that lets us go back to the historical record and uncover the hidden patterns that were secretly there from the very beginning. And this isn't just some fringe interpretation. This is pretty much the scientific consensus. As this commenter puts it so well, you just don't need to bring in something as exotic as backwards in time causation to explain what's going on. It's just quantum mechanics being its usual, wonderfully strange self. But this does leave us with one last, really deep question to chew on. Okay, the past event didn't change. But if our measurement today reveals that a photon that landed yesterday was part of a clear wave pattern, then what was that photon yesterday? Did it behave like a wave? Or does our knowledge today fundamentally change the story we are forced to tell about the past? The physics might be sorted, but the philosophy? Well, that's a whole other can of worms.